In these next couple of videos, we'll be talking about stereo vision. Now, stereo vision is a particular type of photogrammetry. We use it for lots of different applications, for example, in robot navigation. But basically what we're trying to do in stereo vision is do the same thing that we do with our eyes, being able to use two eyes looking from slightly different points of view to measure how far an object is away from us. If we've got one camera, our perception of the world is a bit limited because we've got this 2D representation of a 3D world around us. And what it doesn't give us natively is depth, how far away different objects are from us. As humans, we know there's some tricks that we can use, and we learn these tricks from a fairly young age. For example, we know that in this picture here, we see this man and we see the Eiffel Tower. And we know that we're not talking about some giant here next to a really small Eiffel Tower. We know the Eiffel Tower is quite big and this man is comparatively quite small. And the reason we can have this image is that Eiffel Tower is a long way away and this man is a lot closer in the foreground. And so that's one of the tricks, along with things like the relative size of shadows of different objects. We use, without even thinking about it most of the time, to work out how far away a particular object is from us, inferring the depth of that object. The other thing that we have going for us is at relatively close range, we've got two eyes and we can use the baseline distance between our eyes to work out how far fairly close objects are away from us. And this distance is optimized for about the extent of our hands from our face. So we've got reasonably good depth perception in the first meter or so away from our eyes. Now, when we're taking a picture, what we're doing is converting this 3D environment to a 2D image. And that 2D image, we have a series of pixels in the X direction and the Y direction, and each of those pixels will have a color associated with it. But that particular, each object that we have in our 3D environment will be translated into a flat, and it will be translated to one of those particular pixels in our 2D image. And we can see this in our picture here. Now, what we want to do is have two different cameras looking from two different positions. And those two different positions will allow us to triangulate points between those images. And based on that triangulation, we've matched a point from one image to another image, work out what the depth is from where those cameras were to where that point is in our image scene. So how do we do it? Well, we have a left camera and a right camera, and those cameras will have a slightly different view of the world, just like our left eye and our right eye do as well. We find matching points between those two different images. And based on those matching points, we do a geometric calculation, a triangulation to work out how far our cameras are away from those particular points. So the steps that we need to perform, there's a few of them. Firstly, we have a calibration step. In our calibration step, we're understanding things like how our cameras are positioned with respect to each other. Like, have they got an angle with respect to each other, or are they completely flat? How far they are away from each other, what's our baseline distance between our cameras. And we also want to work out our what we call intrinsic and extrinsic parameters. For example, when we map at a particular depth, what 1 millimeter equals in terms of our number of pixels within our image in our X and Y direction. We then want to do matching, and we're looking at matching features between those particular images. And then we can do our reconstruction, a 3D reconstruction of those particular images. So at the end of the day, rather than having a 2D image where we've got pixels in X and Y, we want pixels in X and Y with the associated color and everything like that. But we want a depth as well, which is our Z direction that we have there. And our Z direction will be a function of X and Y. So for each pixel, we can work out how far away that pixel is from our camera. So one pixel might be 50 centimeters away. Another pixel might be at maybe X 50, Y 70, or something like that. That pixel might be a meter away from our particular camera. So I've mentioned that we need to do stereo calibration, and part of this will be about calibrating the cameras with respect to each other, like how far away they are, what angles they're on. Part of it will be around our intrinsic parameters of our cameras. So looking at scale factors for converting between pixels and millimeters, for example. and working out where the center of our images are as well. Once we've calibrated our cameras, one common thing that's done is we Scanline align our images to make sure image on the left is aligned in our vertical direction with the image on the right, so that we can scan across a particular image and find matching points along that image. And you can see, for example, our Rubik's Cube here, the pixels, although that Rubik's Cube or the book or the cup is being looked at from a different point of view, that Rubik's Cube, if we move along the line, we should hit the same points along that line. Here we've got a basic stereo camera set up with 2 images. Those cameras are mounted in a planar way, so they're completely coplanar with each other, flat. And we need to know the baseline distance between those 2. Now, I've done this in the past with web cameras. You can get 2 web cameras that you mount coplanar with each other and measure a baseline distance between the center of each of those lenses. Now, to compute depth, what we can do is we can choose a pixel in those images, and we can look at it from the left image and the right image. And we'll notice that from the left image and the right image, we actually see that pixel with a different X value. It will have the same Y value because remember we've Scanline aligned these so that we can look right across the Scanline and see those different positions. Now, if we assign one of them, for example, our left one to our 0 position, our next camera, our right one, will be shifted at a baseline distance away. We can then say that we're interested in what that pixel looks like on our particular image sensor. And that will be a certain number of pixels from our center pixel in our image on our left image and on our right image. And you can see in this picture here that we have our left image, we have a great number of pixels from the center of that camera to the right image, which is a lesser number of pixels. And so that left image one is our XL, our right image one, the distance between the center pixel and where we actually see that pixel appear, is XR. And based on that, we can calculate our disparity between these particular images. Once we know the disparity, we can work out, based on our baseline distance and our scaling factor, which is the SX value, dividing it by the disparity, we can work out what our depth is.